Hey wait, do you know that we have a virtual studio in our university for online teaching?
To start with, which university are you talking about?
Oh, okay, it's the Eastern Technical University of Sierra Leone. By the way, we'll be providing online lectures, live streaming some important functions, and also hosting educational programs.
Wow, that would be nice. I can't wait to visit there. By the way, who to meet if I need more insight on the present development of the virtual studio?
Okay, you can meet the engineer Suleiman Greetman Mansare, the Dean of the Engineering and Innovation Faculty, or Mr. Sandavna Kamara, the Head of Information Technology and Computer Sciences Department, or finally you can meet Mr. Joseph Corda, the officer in charge of the studio.
Thank you for the information.
You're mostly welcome.
Hello students and hello everyone. For our today's lectures, we'll be looking at logic. We'll be looking at logic gates. This is a topic in computer programming, and let's try to absolutely understand what logic gate is. So we say logic gate is an elementary building block for a circuit, for a digital circuit. So this is what logic gate is, and for most logic gates, for most of these logic gates, they have one output and two or more inputs. So most of these logic gates have one output and two or more inputs. At any given moment, we consider every terminal. We say every terminal is in one of the two binary conditions. And the binaries are like talking of the zeros and ones, and these conditions may be low, may be in the low condition referring to 0, and the very high condition, let's say high condition, which is 1, and they are represented we say they are represented by a different voltage level. So if we want to understand absolutely what logic gate is, that is what exactly you have to get as an overview. And those logic gates we'll be discussing here may have one output and have two or more basic inputs. So now at any given moment, terminals, and those terminals will be discussed more here, and each of these terminals may be in one of these states, like whether they can be in a very low state, that's referring to that 0, low or 0, and the very high state, which you have that one to be 1, and they are represented by different levels of voltage levels. So now, if this is what absolutely we have, let's try to see the gates we are now discussing here. So those logic gates are classified or categorized into different formats. So let's consider the basic gates. So the basic gates more or less includes, we say, the AND gate, the OR gate, and the NOT gate. So these are the 3 basic gates we have: the AND, the OR, and that of the NOT gate. So let's look at another category. We call it a universal gate. So the universal gate includes the NAND gate, the NAND and the NOR, and the NOR gate. So we look at other type of gates. We say other type, other than these 2. We have, let's say, other gates, which we have the exclusive OR and that of the exclusive NOR, the exclusive NOR gates. So these are basically the various logic gates we have. Of course, this one is considered to be a universal gate because from these universal gates we can get the basic gates. Like for the NAND, we have the NAND here, which is this. We have the OR gate, which is this, and the NOT, which is this one. So let's actually look at those various gates in question here and their symbols, because those are when we are actually looking at how we can develop a digital circuit, like building that digital system. We use those logic gates, or we use the logic gates to construct those systems. So now let's see how each of these gates may look like. So by the way, we say logic gates and their symbols. So the first gate, we are first going to look at the basic gate. So the basic gate includes the AND gate, the AND gate. So now remember, in our intro, we said each of the terminals may include for most of these gates may have 2 inputs and an output. So let's see those gates that may take 2 or more inputs. So for example, we have the NAND gate, which we are going to consider A, for example, and B as input. So to draw the symbol of this AND gate, we draw it this way. You have a straight line and you draw a curve through that towards that straight line. So after which you have an output. Let's say the value of that output, the variable for that output is y. So now, what operation is being performed when 2 input passes through the AND gate? So you multiply the inputs. We say we multiply we multiply the inputs. We multiply the inputs using the operator times. So now let's say you have y to be the variable for the output. So y may now be equal to a times b. Or we can also inscribe this one to be a dot b. So when you multiply these two, the output may now be AB. So this is the kind of operation that is performed when two input passes through the AND gate. So let's look at the other basic gate, which is the OR gate. We say OR gate. So considering the two inputs also as examples, so we have input A and we have input B. So input A has to go through an OR gate, and of course you have to look at the diagram, the difference in that. Here is a straight line, and for here we have a curve. So we call this one to be the OR gate. But the most important thing you have to look at here is the kind of operation that is being performed when two input passes through when the input passes through the OR gate. So here you are adding the inputs. You add the inputs and using the operator plus. So these are like the operands which you have to the input are considered to be the operands. So using that operator plus, you can add these two inputs to get the output y. So y is the output. But let's see how you can get the exact output for these two inputs. So since the operation that is being performed when two inputs passes the OR gate is addition, we have to add these two, that is A plus B. Of course, A plus B, it may also be written as B plus A. But the convention, it is necessary, is important to maintain this order. So instead of saying B plus A, it is important to write it this way. So let's look at the other basic gate, which is the NOR gate, the NOT gate, sorry. So for the NOT gate, you have a single input passing through that gate. Like for example, and that single input may be an expression, for example, having A plus B passing through the NOT gate, and which the NOT gate is being drawn this way. You have this as the NOT gate. So now it can also be a singular character, like you can say A, or you can also say B. But that single input may also appear as an expression, like for example this, as I was saying. But for this example, we are taking A to be the input. Let's say A to be our input. So the value, we are using Y to serve as the variable for the output A. Okay, but what operation that has been performed here? Let's consider this one to be NOT. We say NOT, we're inscribing it. This is AND, this is OR, and this one is NOT. So more or less, we are negating. We take we are negating like taking the negative value of A. Or we can also say taking the complement. We can take the complement of A. Okay, so taking the complement of A. But how can we inscribe? How can we write that one? We can say y is equal to the complement of A can be written as A complement, or we can say A bar. We can write it this way. So either ways, either you write it this way or you write it this way. Yeah, so like we are taking this one to be our method of writing the negative or the complement of our inputs. So if we are looking at the basic three gates are these. We have the AND, the OR, and the NOT gate. So let's look at also the universal gate. For the universal gate, of course, we have two examples. Example number one is the NAND. The NAND gate. But how the NAND gate is being drawn? First, we have two inputs. For example, we have input A and input B. So that input A and input B normally have to go through the AND gate. This is AND, and for example, you have the output Y. But since we are taking the complement of the output AND, initially our AND gate, like for example, this one, if we are using the AND, this one is an AND gate now, without taking the complement of the output, the answer will be AB, because you have to multiply these two inputs to get AB. But if we want to take now the negate this input or the output value AB, we want to negate this one. So this can also be taking the complement of this will be AB bar. But how can we get this bar? Is there we have to put this this dot sign, which we have here, that is stating showing that we are taking the complement of that input. Okay, so with this you have y now would be equal to, because of this, will be equal to A dot B all bar. Or this can, some may even intend to write it as A times B all this. But it is appropriate to get the value or the expression complete, well simplified, I can say. You have AB all bar. So that is how to draw the AND gate, the NAND gate, and the possible expression is this. So let's also look at the NOR gate. So like we are taking the complement of the output for OR. So we are still going to use input A and input B. So we have input A and input B. So for input A and B, of course we know how to draw our OR gates now. So this is how to draw the OR gate. So there's a difference. For the AND gate, you draw a straight line here. For the OR gates, you have a curve here. So this one is NAND. It is NAND gate because of this. And for the NOR gates, we have output Y, and we have to take this one. So this one is NOR gate. So but how can you write this one? It is Y equal to, of course, when two input passes through pass through the OR gate, the operation that is performed there is you add the two operands, like A, or the input. You have A plus B. So A plus B, all complement. So you have this. So we are taking the complement of the output Y, and this also can be written as this expression A plus B, all complement. So any of these are, way to write. You can choose any of these methods. You can write it this way or you write it that way, depending. So let's look at, these are considered to be universal gates. Universal gates. So let's look at the other gate. The other gate is exclusive OR. Exclusive OR. And of course, this is, we already know our OR gates. Our OR gate is being drawn like, for example, taking two inputs. We have input A and input B. First, we are drawing the OR gate, input A and input B. So you have that. Of course, this is our OR gate. So you draw this line, and there you have this. We are not taking the complement of OR, so we just have to look at the output Y. But since we are taking the exclusive value of these two inputs, you draw another line this way. So this is how to draw your XOR. So we say exclusive OR gate. So you have that. But how can you write? Of course, we know the operation that we perform when dealing with the OR gate. So you are adding, like for example, you have this. So the output is equal to A plus B. Like in the case of the NOR gate, it is also A plus B, but because of this sign, we are taking the complement of that. So we have the bar there because of this dot here. So also because of this first line, we have to circle this section. I mean the operator. So that is what you have. And we also have to look at the exclusive NOR gate. The exclusive NOR gate is like having this one as output, and we like having this one negating this output. We've gotten the output for the exclusive OR. So like it is not the value, it's not this output. So we are taking the complement of this output. So how to draw that one? We just have to replicate this one, having A and B as our input. So remember, we are just replicating this one. So you have this, and we have this one with our line this way, and we say exclusive NOR, and we have our output Y. But of course, the one drawn with the exception of this NOR, this one exactly, the value for that is Y. I don't know if you've seen here clearly. So we have Y equal to A B. But if we are now taking the complement of that, so having this symbol this way, this sign here, you take either you put it in bracket and take this, or write it that way, or you say A plus B, all complements. So for more or less, this is how to basically, these are the gates, the various gates, and this is how you can draw the gates, and these are the various expression or the operation you perform. So I want to thank you all for participating, and our next topic will be truth table. We'll be discussing truth table. So I thank you all.